welcome to the Deep Dive. Today, we are undertaking an expedition, really, into the twin frontiers of light science.
Yeah, it's fascinating stuff.
On one side, we've got this quest for, well, ultimate measurement precision. How accurately can we possibly measure something?
And on the other side, capturing time itself. We're talking the fastest events possible in nature.
We're drawing on a pretty rich stack of courses for this one, about 3 decades of quantum optics research specifically on generating certain kinds of light.
Squeezed light, yeah. And we're pairing that with the absolute cutting edge of Attosecond science and ultrafast chemistry.
Right. So our mission today is to try and understand how these new light technologies are letting scientists, well, bypass some of the classical measurement limits we thought were fixed.
And use that to actually observe fundamental quantum processes, as they happen, in motion. And here's the real kicker, the core of today's story, isn't it? The moment these worlds collide, there's this recent breakthrough that actually combined these methods. They're calling it Attosecond squeezed light. It sounds pretty futuristic.
It really does.
Yeah.
And this combination lets researchers get this unprecedented control over how they observe things.
Culminating, as the sources say, in the ability to actually track quantum uncertainty, that fundamental fuzziness of reality in real time.
Wow. Okay.
It's a pretty profound shift, really, in how we approach quantum systems. Yeah. But to really get the scale of it, we need to start at the beginning.
The limits.
Exactly. The fundamental physical limit.
Okay, let's start with a classic roadblock then, the Heisenberg uncertainty principle. Now, when we talk about measurement limits in physics, is this the kind of thing technology will just eventually solve, or is it more fundamental?
Oh, it's absolutely fundamental. Written in stone, as you said.
Okay.
The uncertain principle isn't a technological hurdle. It's a core law of quantum mechanics. It's just how nature works.
Right.
It basically says that certain pairs of properties, they're called conjugate variables.
Like position and momentum. That's the classic example.
That's the one everyone knows, yeah. Or for light, it could be its phase and its amplitude. They're fundamentally linked. Meaning, the more precisely you nail down one, the less precisely you can possibly know the other. There's a trade-off baked into reality itself.
So there's this fixed total amount of uncertainty, and we can't actually shrink it overall. If we can't break the rule, how do physicists sort of get around this wall when they're trying to measure light very precisely?
Well, they cheat, but elegantly.
Okay.
They use a technique called quantum squeezing. So imagine the inherent noise in light, even in a perfect vacuum. There's this vacuum noise.
Right, the quantum fuzziness.
Exactly. And normally that noise is spread equally between those two linked properties, the conjugate variables. We call them quadratures in optics.
Quadratures? Can we think of those like orthogonal aspects of the light wave, like its intensity and its timing?
That's a pretty good analogy, yeah. They represent the two components you need to fully describe the light's quantum state. Amplitude noise and phase noise, basically. In normal light, that uncertainty is balanced. Think of it like a circle on a graph representing the noise. Squeezing uses a special material, a nonlinear crystal usually.
You mentioned those earlier.
Right, to literally redistribute that noise. You reduce the noise, the variance, in one quadrature, let's say amplitude, way, way below that normal vacuum level.
So you take that uncertainty circle and you squeeze it into an ellipse. One axis gets really short. That's your super precise measurement.
Exactly. But the other axis has to get correspondingly longer to keep the total area the same.
So you sacrifice precision in the other quadrature, the phase in this example.
Precisely. So if the variance of the amplitude, let's call it Vx, goes below 1,1 being the standard vacuum noise level, then the variance of the phase, Vp, must go above 1.
All while staying perfectly legal under Heisenberg's law.
Totally compliant. You're just rearranging the uncertainty, not eliminating it.
The sources point to just phenomenal progress here. Over 30 years of work. How much better have we actually gotten at this? Squashing of uncertainty.
Oh, dramatically better. It's night and day, really. Back in the mid-'80s, people were excited to see maybe, 0.3 decibels, maybe 3.5 degrees of squeezing.
Which isn't much noise reduction in real terms.
Not really, no.
Yeah.
It's proof of principle, but small. Now, thanks to much better optics, lower losses, and materials like these ferroelectric crystals, we're seeing measurements up to 13 dB reported. And specific setups, like ones using these things called monolithic cavities with PPKTP crystals, have measured 12.7 dB. Really impressive numbers.
13 decibels.
Hmm.
Okay, for those of us not steeped in quantum optics, what does 13 dB mean? Like in practical terms for a measurement.
It's genuinely transformative. It means the noise in that squeezed quadrature, say amplitude, is almost gone. It's reduced by a factor of about 20.
Wow.
A really famous, successful application is in gravitational wave detection.
Ah, LIGO and Virgo and those guys.
Exactly. Injecting just 6 dBs of squeezed light, which is good, but not even the record, into the GEO 600 detector. It resulted in an 8-fold increase in the volume of space they could survey for gravitational wave events.
8 times the observable universe volume just from cleaning up the light.
By reducing that fundamental quantum noise floor, yeah. This isn't just theoretical, it's actively making our best observatories much, much more powerful.
That's a fantastic example for detection. But the sources also stress this is changing metrology itself, the actual science of measurement.
Absolutely. And what's fascinating there is how far you can push past what we thought were the limits. Take phase estimation experiments. Measuring timing or phase very accurately is crucial for like GPS, atomic clocks, sensing.
All sorts of things.
Right. Using these highly squeezed states, they're called deterministic Gaussian squeezed vacuum states technically.
Okay.
They achieve a sensitivity that doesn't just beat the standard classical limit, the shot noise limit, or SNL.
Which is already hard to beat.
Very. But these squeezed states can actually outperform the theoretical performance of other, more exotic, idealized quantum states.
Yeah.
Like something called a noon state protocol.
Oh, wait, hang on. You're beating the theoretical ideal of another quantum system. How is that possible? What proves that?
Well, the proof is in the measurement itself. There's a metric called Fisher information. It basically quantifies how much information about a parameter, like the phase of the light, you can possibly extract from a given measurement.
Okay, a measure of information yield.
Exactly. And experiments have recorded Fisher information values like 15.8 reciprocal radians squared per photon. Even with real-world losses, around 11% loss in that experiment.
And that number is high.
It's exceptionally high. It means the light is prepared so well, squeezed so effectively, that you're extracting almost the maximum theoretically possible information about that phase variable from each photon you detect.
You've essentially removed the noise from that aspect of the light.
Allowing for incredibly precise measurements, yeah. Even with imperfect equipment, it's quite something.
Okay, so we've got this amazing precision down. Let's switch gears now to the other frontier. If we want to actually watch physics or chemistry happening, what kind of speeds are we talking about?
Well, you got different actors on different schedules, really. The bulky stuff, the atomic nuclei in molecules, their motion, like bonds vibrating or molecules changing shape.
The stuff we usually think of as chemistry.
Right. That typically happens on the femtosecond scale. That's 10 to the minus 15 seconds, or sometimes even slower, picoseconds.
Okay, femtoseconds, still incredibly fast.
Oh, yeah. But the real driver, the truly fundamental action, is the electrons. They dictate everything else.
And they move.
On the attosecond scale. That's 10 to the minus 18 seconds, 1,000 times faster than a femtosecond.
Oh, an attosecond.
So if you want to capture the actual mechanism of a chemical reaction or watch an electron move inside an atom, you need a camera shutter, effectively, that opens and closes faster than that. Faster than an electron can even cross a single atom.
That is almost impossible to comprehend. How on earth do you generate a flash of light that lasts for only, say, 200 attoseconds?
You need a pretty special tool. It's called high-order harmonic generation, usually shortened to HHG.
HHG.
It's a highly nonlinear process. You start with a very intense but normal femtosecond laser pulse, usually in the infrared.
Okay, intense IR pulse.
And you focus it extremely tightly into a gas target. Argon is common, like you mentioned.
Right.
The electric field of that laser pulse is so intense, it literally rips an electron away from an argon atom. That's ionization.
Okay, electrons free. Then what?
Then, because the laser field is oscillating, it grabs that electron and accelerates it back towards the atom it just left, the parent ion.
And it collides.
It slides back into it, yeah. Sure. And when it recombines or recollides, it releases a huge burst of energy. But not as infrared light. It comes out as high energy light, typically in the extreme ultraviolet or XUV range.
And that burst is the attosecond pulse.
That's the essence of it. The process actually generates many high odd harmonics, multiples of the original laser frequency. When these harmonics add up just right, constructively interfere.
You get these incredibly short, isolated XUV pulses.
Exactly, and we've gotten really good at it. We can now generate and fully characterize pulses down to about 200 attoseconds long. There are clever tricks, like something called generalized double optical gating, or GDOG, to make sure you get just one clean, super short pulse.
So with these attosecond strobes, we can essentially make ultra-fast movies of molecules changing. You mentioned chemistry earlier. What's a good example from the sources?
Oh, a really fantastic one involves using these big X-ray-free electron laser facilities, XFELs. They produce very bright, very short X-ray pulses.
Right.
And scientists use them to basically film the combined motion of electrons and nuclei during a chemical reaction. They watch the ring opening reaction in a molecule called 1,3-cyclohexadiene.
Why that molecule?
Because that specific reaction is fundamental to how vitamin D is synthesized in our bodies when sunlight hits our skin.
Ah, okay. Relevant.
Very. And they saw the whole structural change unfold in about 100 femtoseconds.
Still femtoseconds, but you need the fast electrons to kick it off, presumably?
Precisely. And other studies looked at things like chemical bonds breaking, like the carbon-iodine bond and alkyl iodides, using few femtosecond UV pulses to trigger and watch it snap.
That's really cool applied stuff. But
Yeah.
you also mentioned this ties back to fundamental theory. Why is attosecond resolution so critical there?
Well, it goes back to how HHG itself works, that process we use to make the attosecond pulses. The standard model explaining it is called the semi-classical recollision model.
Okay.
And a key part of that model is the very first step, the electron tunneling out of the atom when the intense laser hits it.
The ionization.
Right. The time scale for that initial event is inherently faster than one cycle of the driving laser light itself. It's subcycle.
Ah, so happening within one oscillation of the laser field.
Exactly. And that super fast initial action creates what's called an electron wave packet, an EWP. It's like a little blob of electron probability. The properties of that initial EWP determine everything that happens next, how it moves, how much energy it releases when it recollides.
So if you can't see that EWP being born and taking its first steps.
In an attosecond time, then you can't fully test or refine the fundamental quantum theory that describes it. You need that time scale to really validate the models.
Okay, so we've got supreme quantum precision from squeezing light, and we have supreme time resolution from attosecond pulses. Now let's bring them together. This is the core breakthrough in our deep dive, right? What happens when you merge them? When you apply that quantum-enhanced precision to observing these attosecond dynamics?
This is where it gets really profound. The central achievement, the big headline from these converging fields, is the direct observation and real-time tracking of quantum uncertainty itself.
Tracking the Heisenberg fuzziness. How?
By using squeezed light as the probe in an attosecond measurement setup, they were essentially able to watch how that inherent quantum uncertainty evolves moment by moment with attosecond precision.
Okay, that sounds like an amazing technical feat, maybe a bit of a flex, scientifically speaking, but why is this combination actually necessary? Why not just use a really good, powerful, conventional attosecond laser?
That brings us smack into the reality of where a lot of quantum science operates today. It's often called the NISQ regime.
NISQ, what's that stand for?
Noisy intermediate scale quantum.
Quidsies, okay.
It basically acknowledges that while we're getting much better at building quantum systems, atoms, molecules, qubits, they're still relatively small, intermediate scale. And crucially, they're very susceptible to noise.
So our quantum experiments are inherently noisy.
The systems themselves are fragile, yes. They interact with their environment, they lose their quantum coherence, operations aren't perfect. And on top of that, our measurement tools themselves have noise.
Right, even the best lasers aren't perfectly silent.
Exactly. So if your goal is to push right to the absolute quantum limit, watching an electron move on attosecond timescales, the noise introduced by your measurement probe, the classical noise of your laser, can easily swamp the tiny quantum signal you're trying to see.
So NISQ is like saying, our quantum systems are delicate and our tools are often too loud to hear them properly.
That's a good way to put it. And this is where squeezing becomes not just helpful, but potentially essential for these kinds of frontier experiments.
How does it solve that specific noise problem in an attosecond measurement?
Squeezing fundamentally cleans up the measurement tool before it even interacts with the system. Remember, we reduced the quantum noise in one quadrature of the light itself, below the vacuum level.
Right, the noise inherent to the light probe.
So when you use that squeezed light to probe, say, the electron dynamics, you've already eliminated a major source of measurement noise. the quantum noise of the probe itself.
Ah, I see. So the noise you do measure is much more likely to be the actual physical noise or uncertainty coming from the quantum system you're studying.
Precisely. The true quantum uncertainty of the electron's motion, for example, rather than just noise from your laser or your detector setup.
It's like making sure your microscope lens is perfectly clean and vibration-free before you try to image something incredibly tiny and fast.
That's a great analogy. If you want to track how that electron wave packet, the EWP, evolves in time, you need absolute confidence that what you're seeing is the physics and not just photon shot noise from your probe pulse blurring the picture. So combining a second time resolution with this quantum noise reduction from squeezing, it allows us to isolate that fundamental quantum uncertainty and actually watch its dynamics unfold. This is crucial if we want to eventually achieve fine-grained control and manipulation of quantum processes at their natural ultrafast speed limit.
Okay. Looking beyond just observing, this ability to manipulate and control quantum systems with such precision, that seems like the foundation for a lot of future tech.
Yeah.
Where does this capability lead us, practically?
Oh, almost everywhere in quantum technologies. Squeezed light, as we discussed, is already a critical resource for quantum sensing.
Making better sensors for what?
For almost anything where extreme sensitivity matters. Measuring tiny changes in gravity, magnetic fields, temperature, acceleration, pushing sensors toward their fundamental quantum limits. And of course, this whole effort controlling quantum states precisely, reducing noise, is absolutely central to building functional quantum computers and communication networks. It's all part of the same toolbox, really.
What about pure discovery? You hear about massive particle accelerators probing fundamental physics. Can these kinds of, relatively smaller scale AMO experiments compete?
They absolutely are competing and sometimes winning in certain areas. This is where it gets really exciting for fundamental physics beyond the standard model.
How so?
These ultra-precise AMO experiments, atomic, molecular, and optical physics, were now yielding results that put incredibly tight constraints on theories that propose new particles or forces. Or sometimes they even disprove them.
Can you give an example?
Yeah, a key one is the search for the electron-electric dipole moment, the EDM. The standard model predicts it should be incredibly tiny, practically zero.
Okay.
But many theories beyond the standard model predict a much larger, though still tiny, value. And the latest AMO experiments have pushed the upper limit on the EDM down so low.
That they're starting to rule out some of those new theories.
Exactly. They are probing for effects originating from new physics at energy scales of maybe 3 to 30 tera-electron volts, TeV.
And how does that compare to, say, the LHC?
That's actually a range that's difficult for even the Large Hadron Collider to probe directly right now. So you're getting fundamental physics insights, potentially discovering new particles indirectly from a precision measurement in a quantum optics lab. It's amazing leverage.
That really is phenomenal. Okay, let's swing back to chemistry and control for a moment. If we can observe these ultrafast dynamics so well, can we use that knowledge to actively steer a chemical reaction where we want it to go?
Yes, and the sources give a concrete example of this. It's moving from just observing to actively manipulating.
Okay.
Researchers were looking at breaking apart a molecule called triethylamine. They used what's called open-loop control, meaning they didn't have real-time feedback, but they carefully shaped the laser pulse they used to initiate the fragmentation.
Shape the pulse.
They modulated it, essentially putting specific features or bumps into the pulse profile over time. And they found something interesting.
What was that?
They found that putting specific features into the pulse that were spaced apart by about 2 picoseconds.
Okay, a specific timing.
Right. That specific timing dramatically increased the amount of a particular fragmentation product they wanted to create.
And why 2 picoseconds? Was that just luck?
No, it was guided by understanding the dynamics. They knew from previous studies, or estimated, that the molecule, after being hit by the first part of the pulse, likely passed through an intermediate state, a sort of temporary configuration called a dissociative Rydberg state.
And that state lasted?
They estimated its lifetime was around 2 picoseconds before it fell apart.
Ah, so they timed the second part of their shaped pulse to hit the molecule right when it was in that specific intermediate state.
Exactly. To nudge it or kick it down the reaction pathway that led to the desired product, rather than letting it break apart randomly.
So it's using that ultrafast knowledge to actively control the chemical outcome.
Precisely. It shows how observing the dynamics directly informs our ability to manipulate molecules intentionally. #TagOutro.
Wow. This has been a really mind-bending journey, hasn't it? We started down at the quantum noise floor, figuring out how physicists use squeezed light to get around the Heisenberg limit.
Redistributing that uncertainty, yeah.
Then we jumped to the other extreme, capturing time with attosecond laser pulses, fast enough to see electrons move.
Freezing motion at the ultimate limit.
And then the real power move, combining them, using that quantum-quiet squeezed light to probe those attosecond events, letting us actually track quantum uncertainty itself in real time.
It bridges the precision and time frontiers in a really fundamental way. And if you think about the underlying quantum mechanics, remember what happens during photonization when light knocks an electron out of an atom or molecule?
You create an ion and a free electron.
Right. But quantum mechanically, that process fundamentally creates an entangled pair. The electron that leaves and the ion left behind are intimately linked instantaneously, no matter how far apart they fly.
Entangled at the moment of creation, which happens on these ultra-fast timescales.
Exactly. The entanglement is born in attoseconds.
Okay. So here's maybe the final thought for you, our listener, to ponder. We now have light sources offering this incredible combination, attosecond timing, and quantum-level precision from squeezing.
You can control the probe and the timing like never before.
So the question becomes, can we now use this combined power attosecond squeeze light to directly probe, maybe even verify, the violation of Bell inequalities in these photoionization events, right as the entanglement is created?
Could we actually watch non-locality emerge in real time at its birth? It certainly points toward a whole new experimental avenue for exploring the deepest quantum correlations produced in the universe's most fleeting moments.
A fascinating place to leave it. That's it for this deep dive. We'll see you next time.